So now, first speaker of this session, we have Vivek Farias from MIT to talk about optimal A-B testing.
Thanks. So thanks very much for inviting me. I'm very glad to be here. So I'm going to be talking about A-B testing, and I'll make the notion of what I mean precise in just a bit. But I think we all kind of have a sense of what A-B testing means. And the 20,000 sort of foot view of the talk is really to kind of view this through the lens of sort of an optimization framework. Okay? And what that will lead to is interesting optimization problems, both in sort of the offline setting as well as the online setting. Okay? And so the goal in some ways is more or less to introduce those problems and then say a little bit about the results we have for those problems. And time permits, there's sort of a long list of, I think, effectively open problems that this sort of view leads to. And I'd like to spend some time on that as well. This is joint work with my friend Siamak Molemi, who's at Columbia, and Nikhil Bhatt, who's at Airbnb. So just to get started over here, right? So what's the prototypical A-B test? So the prototypical A-B test, right, is you've got two treatments. It's A or B, and I'm not going to write A or B. I'm going to call them plus or minus 1. You have some population of subjects, right? Let's call that set capital omega. You have some measure of sort of the efficacy of treatment, right? And that's this function y, right? That's a function of little omega and omega, and also whether you use plus 1 or minus 1, okay? At the end of the day, really, what you're trying to get to is some formalization of, is it better to do plus 1 or is it better to do minus 1, right? And so there's a bunch of different measures of that you can propose. And let's say you have a distribution, for instance, over omega. You could propose to talk about the average treatment effect, a very common measure, right? That says, okay, I want to figure out whether using plus 1 is better than using minus 1 on average, or vice versa. Okay? So that's what we'd like to get to, obviously. Now, this is not something we can necessarily compute. So what's the simplest thing we could do? The simplest thing we can do is something that we've been doing probably for, I don't know, 50 or 60 or maybe 100 years, right? Which is a randomized trial. So what's a randomized trial in this setting? The simplest randomized trial, right, is you just do the following, right? Subjects are sort of independently assigned to either plus 1 or minus 1, right? And let's keep it really, really simple. Let's say it's sort of equal probability, right? Subjects get assigned to either plus 1 or minus 1. And at the end of the day, you'll sort of come up with an empirical estimate for this by just sort of replacing each of these with empirical averages. Okay? So that's sort of a vanilla sort of randomized trial. Now, I'm going to sort of spend a lot of time effectively talking about why this isn't enough and what optimizations problems this actually leads to. Yeah?
Just notation, what is omega? Is it
so omega is in cap omega. So a generic element of capital omega is omega. Yeah, so I'll get to sort of what the real issues are, right? Why can't we just stop here? But before doing that, I sort of wanted to give you guys a sense that it's sort of a broad spectrum of problems, even outside of the healthcare setting that we saw, for instance, in the first talk, where this kind of stuff is interesting. So the first talk was all about these sort of clinical trials, just to get a sense, in a cancer trial, I think. Don, if he's around, can probably correct me here. But in a cancer trial, right, the cost of an individual sample is sort of $20,000 to $40,000, right? So these are expensive samples. There's lots of challenges beyond just sort of things like statistical efficiency that were alluded to in the first talk. Siamak and I kind of got into this not so much from this angle, but a couple of different motivating problems. So for one, Nikhil was working on this problem at Airbnb of quote-unquote fixing bad hosts. So I think we all know what Airbnb is. Some of us are probably staying at an Airbnb right now. Right? And a bad host is basically, as the name suggests, when your host does bad stuff, right? The place isn't ready or whatever. And so for Airbnb, they're constantly looking at ways to intervene, right? To sort of make sure that the hosts stop doing that bad stuff. Now, this is actually an expensive, time-consuming, and tricky thing to do. And the way they've actually set this up internally is effectively an experimentation platform where you'll actually try things via an A-B test. So in effect, right? If you want to figure out what the best intervention is, you run an A/B test, and so if you make progress in some of this stuff, you can actually do this. Siamak and I have been spending a good amount of time in the last year with some folks at Amazon, where, interestingly enough, A/B tests are actually being used for inventory management, right? Which seems sort of bizarre, but in a nutshell, what it is the following: the typical approach to inventory management is, has been, you build a nice model, some sort of dynamic optimization problem, you calibrate that model to data, come up with some algorithms, and you kind of go and do that, right? In the case of Amazon, the problems are so complex and the dynamics are so complex that if you started out with this approach of sort of building a model, fitting it to data, et cetera, et cetera, et cetera, you're kind of lost. So instead, their approach is they have a few parameters. Think of it as 5 or 6 parameters that they'd like to tweak, and they constantly want to be on the bleeding edge of the right set of parameters. Okay, so the entire thing is sort of set up as sort of a giant, the giant A/B test, as a giant A/B test. And not just that, right? This becomes so important, that there are effectively companies dedicated almost entirely to providing infrastructure for these sorts of A/B tests, right? So one big giant in that space is APT, that recently got bought by, I think, MasterCard for $1 billion or something like that. Ramesh is, I think, giving a talk tomorrow or the day after. He's chief scientist at Optimizely. He'll tell you more about that, I'm sure. So this has become sort of very, very important stuff. So the question is, again, right? Why can't we just stop at that randomized trial, which seems pretty simplistic, and pack up and go home? The issue is the following. The thing that you're trying to measure, right, the difference, so to speak, between +1 and -1 is tiny, okay, at the end of the day. So think of this as follows, okay? So, let's say you want to run an A/B test on what size font is appropriate for an ad online, right? The impact of the font, first off, it might not have an impact. And if it does have an impact, it's likely to be tiny on an already really small number. Okay, so the signal that you're trying to estimate is actually fairly weak, right? And then, of course, just sticking with that example, right, of somebody converting on an ad online, an ad's not going to convert just because of the font, right? It's going to convert for a plethora of other reasons. So the efficacy, the thing that you're trying to measure, is impacted not just by the treatment, but a huge number of covariates, okay? And in the examples I was telling you about, earlier, it's not unusual to find that, once you kind of categorize those covariates, you're looking at, 1,000 or even 5,000 dimensional vector, right? So you're looking at a large number, of covariates. And so when this happens, the natural sort of thing that comes up is statistical efficiency, right? If I just kind of randomly sampled and allocated to 2 groups, that's unlikely to be sufficient, and I'll give you a stronger sense of that as we go along. So okay, so if we're going to sort of go for efficiency, right? Intuitively, what do you want to do? So intuitively, you want to do something that's referred to as stratification. And what stratification is nothing but, at the end of the day, after you're done with your allocation to +1 and -1, and you look at the distribution of covariates in either of those groups, you want those distributions to look really, really similar, okay? Now, if you have 2 covariates, it's pretty easy to see that this is a very straightforward approach, and indeed, this is kind of a textbook approach of doing things, right? But as soon as you have a slightly larger number of covariates, even let's say you get to 5, right? Doing something like stratification doesn't necessarily make sense anymore. So what does one do? Well, turns out there's a huge literature associated with this, right? And we kind of stumbled along discovering this literature over the last few years. It's fair to say the literature is actually gigantic, and so what I'm showing you over here is kind of a little bit of sort of my bias plus the literature, right? So you're getting to see the literature through my biased eyes. But nonetheless, right, I would actually track all of this back to experiment design, right? So in the last talk, Don sort of referred to Fisher in the 30s, and really I think a lot of this stuff, goes all the way back to sort of this seminal textbook that he wrote in the mid-30s. More sort of modern treatments of that topic, right? It's so broad. There's this book very nice book actually by Puckelsheim on experiment design more generally. And then for A/B tests, so what I'm thinking of as A/B tests, there's this sort of very comprehensive sort of book by Baldi Agostini, right? So what are the problems, though, that one kind of formulates over here? So there's sort of 2 classes of problems, right? And we're sort of talking about optimization now, right? So this is sort of the offline problem. And if you focus on the offline problem for a bit, the idea with the offline problem is you collect all of your subjects before you make an assignment. Okay, so you register all of your subjects and don't make an assignment to them. So you register all of them first, right? And having then registered them, you want to split them into sort of these two groups to kind of best balance the distribution of covariates in those two groups. So this is also fairly old. This is sort of a nice kind of paper for applications of this sort of stuff. It's more in the social sciences than anything else. And more recently, folks have actually been positing and proposing combinatorial optimization problems to solve exactly this sort of problem. So Jose Zubizarreta is a statistician at Columbia, and he's written sort of a series of papers where he proposes a bunch of these mixed integer programs to actually solve this. It's actually gotten a huge amount of excitement and buzz going in this world, right? So that's the offline problem. What I'm more interested in is today, although I'll say something about the offline problem, is the online problem, right? So the online problem is one where you don't get the chance to collect all of your subjects a priori before making the assignment. Rather, a subject walks in, and given all the information you have thus far, which is the existing allocation thus far, you decide whether you want to put that subject in +1 or -1. Okay? So turns out that, again, there's sort of a fairly rich literature associated with this problem, starting all the way back with sort of Brad Efron in the early 70s. So Brad proposed this thing called the biased coin design, right, in the early 70s. If you just Googled biased coin design, you'll probably get 1,000 papers now that have flowed from this sort of one seminal paper in the early 70s. And his paper was kind of motivated by a very, very simple sort of need, right? His paper was motivated by the need of preserving balance at any point in the experiment between the number of people assigned to +1 or -1, right? So yeah, if you assign +1, -1 uniformly at random, you get this sort of square root n type difference between the two groups. His idea was actually, maybe what we can do is effectively using something like an EARN strategy, make sure that we kind of preserve balance between the two groups as we go along, but at the same time have randomness in the process. So it's hard to manipulate. Now, what's ended up happening is that idea of Efron has led to a vast literature where, as opposed to just balancing the number of subjects in the two groups, people have tried to come up with heuristics, algorithms, to effectively balance not just the count, but also a variety of statistics, typically first and second order statistics, of the various covariates in the two groups. Okay? And all of these papers that I'm talking about over here are kind of fundamental in that regard. Now, one of the interesting things about really all of this work over here is you pick up any of these papers, they follow the following kind of trajectory, right? So the paper will set up the problem not unlike how I've set it up just now. They'll present an algorithm. The algorithm will typically be some sort of index rule. Okay, so they'll present that index rule, and then they'll present a bunch of analysis as to why that index rule is good. And there's this paper by Atkinson in 2015 that I was looking at last night as I was putting together the lit review. He actually does this compendium of all the index rules that exist, right? And I counted like 30 in his paper, right? So there's a huge number of these index rules, all kind of analyzed after the fact. And in some sense, it kind of leaves this uncomfortable feeling of what are we actually trying to do? What's the actual problem here? How do we actually come up with something that makes progress in a very sort of principled kind of way? And that's really one of the things that I'm going to try and accomplish. Okay, so that's kind of background. I'm not going to get into the talk proper. Okay, and the plan for the rest of the talk is to kind of set up a model. All right, so I'm going to set up a model. You'll have to take my word for it that the model is in some ways very, very standard to this sort of literature over here. Having set up the model, I'm going to then propose two problems, an offline problem and an online problem, and we'll discuss them in turn. Okay, so that's kind of the idea. And then, as I was saying, if time permits, at the end, I'll show you some results with sort of real-world clickstream data, and I'll talk about a few open problems. Okay, so as I said, the first thing we're going to have to do is assume some sort of functional form for y. Okay, if you don't have a functional form, it's very hard to make progress. And in fact, sort of this nice Annals of Stats paper from a few years ago that kind of formalizes that. So what's the sort of the canonical functional form that actually gets used, right? So this is effectively the canonical functional form with covariates, right? It's trivial. It's a linear form. And what it's saying is the following, right? Little k over here indexes subjects, right? So subjects are indexed by little k, right? Y sub k is the treatment effect that you'd observe for the kth subject, right? And that's a function of how you treated that subject, right? So it's a function of xk, so was it +1 or -1? And it's also a function of all of the covariates that that subject actually comes with, okay? So it's a function of this zk as well. And for what I'm going to do next, zk is going to be a p-dimensional vector, and this noise over here, this epsilon over here, I'm going to assume is independent of everything else. It's exogenous, okay? Yeah.
What is k? No, zk times k.
Yeah, so k is indexing subjects or patients or impressions or whatever you want to call it, right? So remember we said where a patient comes in, think of the canonical example of a patient comes in, you assign the patient a treatment. I'm indexing those patients by k. Okay?
What's kappa?
So kappa is an unknown vector, right? So this is, okay, so very good, right? So what do we know in this model? So other than the fact that it's linear, we know nothing, okay? So we don't know what kappa is, and we don't know what theta is. Okay, so theta is a scalar, kappa is a p-dimensional vector, we don't know either, okay? Now, if I write things down this way, what's the average treatment effect, right? Well, in this particular case, right, the average treatment effect is simply 2 theta. So really my goal at the end of the day is actually to estimate what theta is, right? So let's do the following, right? Let's say that what we did, right, and I'll justify this in a second, but let's say we did this, okay? Let's say that what we did is we came up with some allocation, right? So we have all of these impressions or treatments or whatever it is coming in. We have a total of little n of them, right? We allocate each of them to either +1 or -1, okay? We get to observe all the outcomes, which is y, right? And then what we do is, let's say we decide to learn theta by doing least squares, okay? Because for each guy, I've got the covariate vector. I know whether it was +1 or -1. I observe what ended up happening. I do least squares. And from least squares, among other things, I can pick out theta, right? If I did that, right, the variance of our estimate of theta is then simply right, sigma square, which is kind of this noise you can't get away from, right? It's the variance of the exogenous noise, divided by this quadratic form in x. I'm not going to interpret the quadratic form yet because it's got a nice interpretation that'll come by later, right? For now, let's just think about it as there's some quadratic form in x, and this matrix P over here is a function of the covariate vectors for each of the observed subjects so far. Okay? Everybody with me? Yeah? Okay, good. So let's say we had this, right? And of course, there's a lot left on the table, right? Why are we doing least squares, et cetera, et cetera? We'll get to that in a second, right? But let's say we have this, right? One of the things you might want to do is minimize the variance, right, of your estimate of theta, or equivalently, maximize efficiency, which is efficiency is the reciprocal of this quantity, right? So this leads to immediately sort of an offline problem, right? So the first offline problem the offline problem we can propose, right, is what I want to do is come up with an allocation of these subjects to +1, -1 that maximizes the efficiency of my estimate of theta. Okay, so that's one thing I could do, and that's the offline problem. It's offline because solving this requires I be able to see z, right? So I'll need to actually observe all of the covariates of everybody coming in before I can solve this. The online problem, which is a little bit hairier, is the following, right? So at the end of the day, I care about the same metric, right? I care about the efficiency of my estimate, but now I can only talk about the expected efficiency, and this expectation is over the process z, right? The expectation is over the process of covariates that actually arrive over time, z, right? So what am I actually saying over here, right? So what I'm saying over here is that as I actually assign to the kth guy, right, the only information I can use is the allocations that I've made thus far and the z vectors that I've observed thus far, okay? Interestingly, you'll also notice that I'm not allowing myself to observe y's, right? This is something that actually came up in the last talk, right? Do we actually observe the outcome or not? We don't observe the outcome over here, right? You just observe what you allocated and what the covariates, what these covariate vectors were up to that point in time. Okay? So offline and online problems make sense? Yeah.
One short question. For the offline, I can see that maximizing the quadratic form is like minimizing 1 over the quadratic form, which you're interested in.
Yeah.
In the online problem, I don't see why it's equivalent.
It's not.
Okay.
No, it's not. Right? So in some ways.
Why aren't you trying to minimize the expectation of 1 over?
Yeah. So very good, right? So I guess we had to start somewhere, correct? And in some ways, the idea was come up with an optimization problem where 2 things happen. 1, we can kind of make progress and talk about what's optimal, right? And 2, kind of put all of the other stuff that exists in the context of the problem. So it turns out when I actually look at efficiency, I get both of those things. When I look at the expected value of 1 over the thing, I don't. So it's sort of a, it's a formulation choice that we've made over here. But it's not like one is any more fundamental than the other. Okay.
Vivek, you could presumably bound one in terms of the other.
Yeah, you could.
But it's too loose to be useful.
Yeah, so at the end of the day, you're actually dealing with quantities that are on the same order as what you would get if you tried to actually bound one over the other, right? Because you need some low variance kind of stuff happening. So,
And
yes.
why don't you use the Ys that have been observed before? Wouldn't help?
Good. So in fact, hold that question for the next slide, right? So really, let's actually just step back for a quick second, right? So what does the Cramer-Rao bound tell us? So the Cramer-Rao bound would tell us, right, that provided x and z were exogenous, right? That is to say that x and z are independent of the epsilons, right? Then really, the best estimator that I have for this theta, this treatment effect that I'm trying to learn, is in fact least squares, right? And the expression that I was trying to sort of minimize in some sense is in fact the variance of that best estimator. If I stuck with this assumption of throwing away the observed y's, right, I can now at least start to talk about what an optimal estimator is and what an optimal allocation is in light of that estimator. Now, this actually leaves open a bunch of interesting questions, right? So if you actually allow yourself to observe y's, it's really unclear how to even pose the question of thinking about the optimal estimator. So indeed, I think that's an interesting question, right? If you observe y's, you could presumably think about doing all sorts of sort of biased estimation techniques. Very difficult to actually think about even sort of starting out with saying what is the optimal estimator in that setting. Okay, so that's what we're doing over here. We're not getting to look at what the y's are. Okay, so because of that, right? Because all I get to look at is the x's thus far, the allocations I've seen thus far, and the covariate vectors thus far, I can actually say that, well, actually what these problems are doing is maximizing efficiency for the best unbiased estimator. Okay? Yes?
So, I mean, given that you have done this in practice, I mean, if you did use the Y and you did something active with the Y, how much would it help? I mean, do you have...
So I have literally like one data point on that, and I'm afraid to kind of talk. So the one data point I know of where you can actually do this, where I've sort of seen impact, is actually using A-B testing in execution of financial trades against sort of dark pools and things of that nature, right? And over there, you definitely want to observe the Y, right? It's what ended up happening. It's not clear to me whether this formulation is actually the appropriate formulation over there. I would almost want to say that some kind of bandit problem is the appropriate formulation over there, because over there, you care about 2 things, right? You care about learning the treatment effect, theta, but you also don't want to make losses as you're kind of learning theta, right? Over here, I really just care about learning theta at the end of the day. Makes sense, right? All right, so we've posed 2 problems, and now I want to solve these problems, okay? And that's the rest of the talk. So first off, the offline problem is actually easy, right? And that's because PZ-perp is a projection matrix, so it's positive semi-definite. So at the end of the day, we've got this nice Gummins-Williamson type approximation algorithm for it. You can come up with a de-randomization of it if you're worried about the noise introduced by the randomization. And I don't care about constants because I'm talking about statistically optimal over here. So doing the offline problem is actually easy. And in fact, the one thing that I find actually interesting over here is it's easy only in this kind of very specific setting, right? So other sort of ad hoc measures of covariate imbalance, right? So I alluded to some of these mixed integer programming papers that I was talking about earlier. You can't get to sort of, at least as far as I can tell, you can't necessarily get to an efficient approximation algorithm in those settings. So there's this sort of nice thing that happens over here that when we talk about this particular formulation, we get an offline problem that's actually easy. So I don't really care nearly as much about the offline problem, but one of the things you can do in this setting is ask the question of, well, does optimization actually matter? Right, so what difference does optimization make? And in the offline setting, it's kind of easier to think about the impact of optimization. So I'm going to take a digression for a couple of minutes and actually talk about what does optimization do for you over here, right? So to talk about the value of optimization, right, vis-a-vis, let's say, randomization, right, let's actually construct a generative family, okay? So I'm going to pick a very simple generative family of covariates, right? The first component of this covariate vector has to be 1. If it's not 1, you can't necessarily think about this as A-B testing. Otherwise, you could assign everything to A and still learn the impact on B. Okay? So the first one is always going to have to be 1. And that's just sort of a convention. The rest, it's just a normal random vector. Okay? So assume that these covariate vectors are sort of normal random vectors. And really, I'm kind of, as I said, right, interested in the setting where P is actually really large. So in fact, what I'm going to do is make P, in fact, as large as it can be, which is n minus 1. Right, in this setting for everything to kind of make sense in the context of what I talked about, and say, well, what's the difference between optimization and randomization? Okay, so here's a simple calculation, right? So if you randomized, right, I just randomly assigned to +1 and -1, and I asked myself, well, what's the efficiency, right, of what I just estimated, right? It looks like this, and in particular, what that's saying is that, right, if P were n minus 1, right, so consider this ensemble of instances, right, where you grow the sort of the dimension of the covariate vector as you grow the number of samples, right? If P were n minus 1, this is an extreme where you actually wouldn't learn, right? You want the efficiency to grow like n, and it's not going to grow like n, right? Now, what happens if you randomize in this same setting, okay? So as I was saying, ideally, we want this quantity to grow with n, right? So the question is, can optimization in this very extreme setting allow for learning? And the surprising answer is actually yes, right? That is, taking that same example that I just talked about, we can actually characterize the optimal value of this optimization problem over here, right? And in fact show that this efficiency is going to sort of scale like n, okay? Which is sort of the best possible scaling that you could hope for, right? So for large P, P is n minus 1, so it's as large as it can be, the efficiency under randomization is order 1, but as you don't learn. And with optimization, it's omega n. Okay, so this is kind of a very sharp sort of example. In reality, you'd imagine that it's going to be weaker, but it kind of brings out this difference between optimization and pure randomization. Okay.
What do you mean by Pn? It's increasing with n?
Yeah. So for this to make sense, right? I'm considering an ensemble of problems. In that ensemble, as n grows, P is allowed to grow with n. Right? If P were fixed, really all bets are off, right?
You've got P like order n.
And so, exactly. So in fact, over here, as long as Pn is smaller than n minus 1, you're going to get growth with n. And at n minus 1, as we saw with that randomization, you wouldn't get growth with n, you'd get a constant. Okay, so let me actually skip this. Okay, so I want to actually talk about the online problem, right? And this is where I want to spend some time. So we just spoke of the offline problem. The online problem is effectively the same thing, right? Except that, as I said, we've actually got to make these allocation decisions on the fly, step by step, right? So first guy comes in, I've got to make an allocation decision. For the second guy, I get to look at the allocation I made for the first guy, his covariate vector, and the covariate vector for the second guy, okay? So that's the problem I want to solve. It's very hard to make progress on any meaningful progress on this problem without assuming a distribution, so to speak, for z. So for what I'm going to talk about next, I'm going to assume right, that the z's, each of these z's, are independent vectors from an elliptical distribution. Okay, so basically all I need is spherical symmetry. Okay, so just think of it as multivariate normal if you like, right? But it doesn't have to be multivariate normal. Right, you could have bimodal sort of magnitudes for these vectors. Okay, So I'm going to assume that they're independent vectors from an elliptical distribution. And the punchline of this whole thing is I'm going to provide a simple, computationally efficient, and approximately optimal algorithm for this problem. Okay? So right at the get-go, right? Oops, sorry. So right at the get-go, right? This is pretty nasty looking, right? So if you actually look at if you look at this quadratic form over here, it doesn't separate over time in a clean way. So the first step that we're going to try and make, right, is to somehow simplify this objective. So let's actually stare at this objective for a quick second. Okay, and understand what this objective is telling us to do, right? So really, this is just me writing out what X transpose Px is, right? And what I want to do is interpret some of these quantities, okay? So what is this, right? So gamma n inverse over here, right? What is that? You can think of that as being an empirical precision matrix, okay? So gamma n inverse is an empirical precision matrix. That's all it is, okay? The empirical precision matrix that you get from looking at the n observed covariates so far, okay? And what is this quantity, what is this summation over here? The summation is a very natural quantity, right? Remember that the x's were +1 or -1, right? So what this is doing is, this is adding up all of the n covariate vectors according to whether you set them to +1 or -1, right? And now if you think about it intuitively, we wanted balance, right? So if we want balance, we want these covariate vectors effectively to kind of balance out. We'd want this sum over here to be small in some sense, right? And what this functional form is doing is it's encouraging exactly that, okay? So it's saying that basically, right, we'd like this quadratic form effectively in this covariate imbalance over here, and we'd want to minimize that, okay? So that's what's actually going on. So the first step I'm going to make, and it's going to be heuristic for now, and I'll formalize it on the next slide. I'll prove a theorem on the next slide, right? Let's say we pass to the following limit, right? Which is basically, look at the empirical precision matrix over here, right? And just replace it by its limit. Okay, now this is problematic, right? Because really I want to consider settings where P actually grows with n, right? And I'm just sort of thinking of things in terms of the law of large numbers over here. We can't do that. The second issue is, right, in replacing this quantity by some other quantity, we'll have to actually worry about how smooth the control is, right? The optimal solution is with respect to this objective. So it's a bit delicate, but we'll get to that when we do. Okay? So first step, take this empirical precision matrix and replace it by its limit. Okay?
Vivek.
Yeah.
When you're actually doing the allocation, you're only counting the number of assignments to -1 +1. You're not actually using the feature vector value.
Oh no, I am. So I'm using all of them.
Well, incoming you're using.
No. So, okay. So good. Sorry.
But the allocation rule, are you using literally that?
Let's come back to it. Right? Okay. So basically, right?
Are you using it? But my question was, are you literally using it as xk, zk, sum?
So I've not talked about the optimal problem yet, right? So the optimal problem is presumably this very nasty control problem that depends on the entire sequence thus far, right? And you'll see in a quick second that after I make this approximation, I'll actually reduce this to a dp, but it's still a high-dimensional dp. Okay? So I see where you're going with this, right? I see where you're going with this. But the point is that in generality, you need the sequence. Sufficient statistic is not obvious, so to speak. Okay. Okay, so if I made this substitution, right, I'm going to rewrite this in it's slightly more compact notation, right? I'm actually going to look at this objective. It's replaced by, right, two quantities over here, right? One is this quantity little delta n squared, right? That's actually counting the imbalance in the number of assignments to either group, right? And the second is, this is what Balaji's thinking of, right? I look at this quantity capital delta n. I'm summing up the covariate vector, right? The imbalanced covariate vector thus far. And I'm hoping for that to actually be small at the end of the day, okay? So what I'm saying is I want to approximate this with this. Now, that raises two questions. So first of all, why would I want to approximate it? Short answer to that is it actually lets me fall back on some dynamic programming methodology. I'm still not home free, but it'll at least let me start thinking about that. The second thing is I can show that actually solving this problem is in fact very similar to solving this problem. So in particular, this is sort of the the surrogacy that we're proposing, and what we can say is effectively, right, that if we solve this surrogate problem, came up with an optimal solution to the surrogate problem, okay, it's an epsilon approximation to the original problem that we actually started out with, okay? Now, important over here is that we've got to, as I said, let p grow with n, and in fact, we do let p grow with n for this result to hold, okay? So really, all I've done so far, one second, Bobby. So all I've done so far is I start out with that online problem. I said it looks a little messy, and so I've made a simplification. And I've come up with this alternative problem over here. And all I'm saying is that when I solve this alternative problem, the solution I get is actually close to the original problem. Bob, and then I'll come back to Kamesh.
In the online problem, I had been assuming that the matrix sigma was unknown to the decision maker. And so I'm confused as to why it's without loss of generality to assume that it's the identity.
Yeah, good. So, good. So I'm going to have to assume I know sigma. Now, for all of the examples that I was actually talking about, that's actually really reasonable, right? Because this is a function of the population that I'm actually sampling from. So think of it as like, okay, I want to actually figure out the efficacy of a particular ad on Facebook. I'm trying to learn the efficacy of the ad. The covariate distribution is well known. I have thousands and thousands and millions and millions of samples of that. So I'm going to actually assume that sigma is in fact known. Okay? Kamesh?
So the related question is, you're assuming that the samples are coming IID from this distribution of zk's, right?
Mm-hmm. Yes, absolutely. Absolutely.
But
Yeah, absolutely. Yeah.
sigma is dimension p, is it?
It is. Yep. Actually, it's p minus 1, right? Because
Okay, yeah.
I'm taking out the 1 for the constant. Mm-hmm. That's right. All right. So I've come up with, I went from one hard problem to a different hard problem, which is this one. All right. So first off, right, let's observe that at least I can sort of write down a dynamic program for this problem, right? In particular, it's a dynamic program that admits, right, a fixed dimensional state space representation, right? So the state I need to actually track over here is little delta k. That's a number, right? That's the imbalance between the two groups. And then capital delta k, which is the imbalance in the covariates between the two groups, okay? This is still not easy because we're left with a high-dimensional dynamic optimization problem. It's fixed dimensional, but high, right? So it's a p-dimensional dynamic optimization problem. Right, and just to kind of complete that loop over there, right? This is correct because really all I care about to actually compute this is I just need to know little delta and capital delta. I don't need the sequence. And so that was actually the whole point of actually taking out that empirical precision matrix and putting the real thing actually in there. I wouldn't necessarily be able to play this game if I didn't do that. Now the next step is actually a state space collapse, okay? Which is that what I want to do is go from a p-dimensional dynamic optimization problem to a low-dimensional dynamic optimization problem. That's what I'm going to do next, okay? So as we've kind of summarized thus far, we got to a DP that state space, whose state space was little delta and capital delta, right? That's in p dimensions. It turns out that I can actually solve, it suffices to solve a DP in 2 dimensions, okay? Namely, it suffices to track little delta and just this weird norm, it's called the Mahalanobis distance, of capital delta, okay? And what's behind this? So what's behind this is actually something fairly simple and serendipitous, okay? So effectively, it just relies on this. And you'll see why this very simple calculation will actually make a difference in a second, okay? So the idea is, right, if I look at the inner product of any multivariate Gaussian random variable, right, with an arbitrary capital delta, right, in this weird kind of inner product where it's important that the sigma over here match the covariance matrix of the z, right, then in order to know the distribution of this, I don't need to know capital delta. Okay? I can write down the distribution of this quantity without knowing capital delta. All I need to know is this Mahalanobis norm of capital delta. Okay? So that's a simple key observation. right? It works only if it's in this inner product, right? And you'll see how this kind of serendipitously helps us in a second.
Is there you are using the elliptical distribution?
Yeah, absolutely. This is exactly where that comes in. Okay, so how are we using that, right? So we're using it as follows, right? In fact, let's kind of play this movie forward, right? Let's look at sort of the induction argument over here, right? So at the penultimate time step, at time n, right, you're at some state little delta n minus 1, capital delta n minus 1, okay? And I've kind of written it down in its gory detail over there, right? Now, really at time n plus 1, which is the terminal state, right, what's your state going to be, right? Well, you're going to take that nth sample that arrives, and you're either going to assign it to +1 or -1, right? Which takes little delta to little delta n minus 1 plus cap xn, right? And it's going to take capital delta to capital delta n minus 1 plus the covariate vector with the appropriate sign, right? Was it +1 or -1, right? Makes sense, right? Okay. Now, this was the last time step, right? And we incur our only kind of terminal cost in this last time step. So the terminal cost was this quantity over here, all right? This should be a squared norm. I'm missing a square over there, right? So that's not a problem. Now let's actually think about this, right? If I expand this out, what's it going to depend on? It's going to depend on this Mahalanobis norm of delta, right? It's going to depend on effectively, the covariance matrix for z, right? And it's going to depend on that same inner product that I showed you in the last slide, okay? And if you remember, that inner product actually depended on delta only through its Mahalanobis norm. So in particular, right, using the insight from the previous slide, right, in distribution, this quantity, right, I can write down this quantity knowing just the Mahalanobis norm of capital delta n minus 1, okay? So what was sort of serendipitous about this was a couple different steps, right? One, it feels really hard to kind of pull this off without actually replacing the empirical precision matrix with its precision matrix, okay? Two, this goes back to sort of an early question that was asked, right? The actual formulation at the at the end of the day. Should you go with maximizing efficiency, 1 over variance? Why even look at efficiency of variance, right? It seems like in this particular case, this sort of works out really, really cleanly, and that's kind of the serendipity of sort of what's happening over here. Okay. So as I said, at the end of the day, you got a 2-dimensional optimization problem. Now, what I really like about this is the following. So if you go back to that original literature, right, that I pointed to at the very start, people think about all sorts of generalizations of the A-B testing problem that we started out with. So let me name 2, right, that are actually pretty important. So one is having a budget, right? So I was talking about 50-50 over here, right? If you talk about having a budget, you say, well, actually, right, I can only assign 3% of my impressions or 3% of whatever to this test, right? The space of heuristics is actually pretty new. There's literally 4 or 5 papers on this topic that actually extend the existing heuristics with some sort of hack, right? If you want a budget over here, it actually flows from the same kind of dynamic programming argument, okay? Another version of the problem is, and this is actually important in settings where you care about manipulation, maximizing not just efficiency, but also caring about how unpredictable your assignment actually was, okay? So it turns out there's actually a way people actually think about this in hindsight, like how unpredictable was the trial that you actually ran. And again, solving that problem ends up becoming a low-dimensional dynamic program. Okay? So really, this sort of simple dynamic programming methodology lends itself to lots of variants of the problem. Let me actually skip this. This actually just results on this Yahoo clickstream data set, and all it's really showing is effectively that if you optimized over sort of just a randomized trial, there's a lot of power, to the optimization. What I wanted to talk about, just in parting, is sort of some of the open problems that this actually leaves, right? So I think first off, one is proving correctness for generalizations. So once you actually write down this dynamic program like I did, it's actually pretty easy to start writing down dynamic programs for all sorts of variants of this optimal A-B testing problem. The issue is the theorem that I showed you, where we replaced that empirical precision matrix with the exact precision matrix. That theorem is a lot of work, and every one of these generalizations actually requires revisiting that theorem to actually think about whether it works or doesn't work. So I kind of think about this as sort of low-hanging fruit, though. Another one, and I think this is much more important, is thinking about models where you know a priori that your dependence on covariates is sparse. Okay? So I wrote down that linear model, right? And I said nothing about kappa. Kappa could be anything. But what if, for instance, you knew that actually the real kappa is in fact sparse? So I think that's actually a very, very realistic problem, right, in a lot of these settings. And what that requires is effectively thinking about the original least squares problem I talked about, and as opposed to viewing it as a least squares problem, you'd need to think about a regularized version of that problem. Now, if the regularization was ridge regression, so you have a 2 norm, I believe that a lot of the results I talked about actually go through pretty simply. But if it's the lasso, which I think is more important for sparsity, then it's really unclear what to do. So the third thing, I made this assumption of elliptical distributions. One interesting question is whether we can sort of employ some sort of CLT to say that, well, in reality, we don't really need that. We don't really need that requirement. And then finally, I was looking at everything in sort of in this sort of dynamic programming setting. I really don't know what sort of the appropriate sort of adversarial results would be for the same online problem that I talked about if you wanted to think about those covariate vectors as being from some general adversarial family. So that's all I had. I think I'm good on time too. So.
You can set up, you can take like one question maybe. Go ahead.
Is there a method for doing inference after this?
Yeah.
Without the randomization?
So that's another big set of open problems. So, you want this? So basically, right, one thing you could do is, so you think about hypothesis testing, right? After you do it.
Sure.
Good.
Yeah.
So after you do something like what I just talked about, the natural kind of hypothesis test would be to do some kind of permutation test, which you could easily do. But I think the real sort of thing, and this leads to a different formulation altogether, is insisting that when you make allocations in pairs. Okay? So that is to say, right, at the end of the day, after you've observed an even number of guys, right, they've all been actually put together in pairs. If they've actually been put together in pairs, now at the very end of the day, you could actually randomize by flipping a coin, right? And that sort of after the fact thing makes hypothesis testing much easier. But the optimization problems that I talked about over here also seem to get harder.
Okay, thanks, Vivek. Now next we have Balaji Prabhakar from Stanford University, who's going to talk about stable marriages in metric spaces.